Something just streaked through our solar system at 220,000 kilometers. Not a meteorite, not a wayward asteroid, but something that shouldn't be here at all. On July 1st, 2025, telescopes in Chile at the KSK Formosa spotted a faint point moving strangely far too fast, far too straight. When they traced its path backward, the numbers defied all reason. This thing came from outside, from somewhere far beyond the stars. It had been traveling for billions of years before our sun even knew we existed. This is 3I, Atlas, the third visitor from interstellar space ever detected. And its journey through our solar system is revealing something that changes everything we thought we knew about what's out there in the dark. If you value documented space science like this, please subscribe. It's the best way to support our work. Also, comment below and tell us which city you're watching from. This script was researched and is based on facts using sources from NASA and the European Southern Observatory. Now let's get back to the story. The Atlas telescope in Rio Hurtado detected it first. Magnitude 18, barely visible, moving through the constellation. Serpent Cauda close to the galactic center. But within hours, something was clearly wrong with the calculations. The object was designated A11PL3Z, a temporary name for a temporary visitor. Except this visitor was moving at 61 kilometers per second, relative to our sun. To put that in context, the fastest human-made object ever built, the Parker Solar Probe, maxes out at 200 kilometers per second when it's diving toward the sun with gravity assist. This thing was doing 61 kilometers per second in the cold vacuum between stars. The numbers just kept getting weirder. Its orbital eccentricity measured 6.1141. Any object with an eccentricity greater than 1 is unbound from our sun's gravity. Jupiter can slingshot a comet up to about 1.05 at most. Previous interstellar visitors 1I, Oumuamua, and 2I, Borisov, registered 1.2 and 3.4 respectively. 3SA, Atlas, hit 6.141, the highest eccentricity ever recorded in our solar system. Its trajectory looked like a straight line, not the curving path of something falling towards the sun, but the track of an object just passing through with no plans to stay. When astronomers traced its path into the past, they found it came from the general direction of Sagittarius, the center of our galaxy, the thick disk where ancient stars orbit on inclined paths above and below the galactic plane. Pre-discovery images dated back to June 14th. The Zwicky Transient Facility in Palomar had been tracking it without knowing what it was. The same was true for Atlas telescopes around the world. All the data pointed to the same impossible conclusion: this object had been adrift in interstellar space for 3 to 11 billion years. It was older than most of the stars in our neighborhood, perhaps even older than our own solar system. But the real shock came when they took a closer look. Hubble locked onto the target on July 21st, 445 million kilometers from Earth. The image showed something no one expected. A teardrop-shaped cocoon of dust and gas, a brilliant nucleus wrapped in a massive coma that stretched for thousands of kilometers. This wasn't a dead rock tumbling through space. It was an active comet ice turning to vapor dust getting pushed by the solar wind. The James Webb Space Telescope confirmed it. Carbon dioxide, water vapor, carbon monoxide. Classic comet chemistry. The Swift Observatory detected hydroxyl radicals and water. The Very Large Telescope in Chile found cyanide gas and atomic nickel vapor on August 14th and July 20th, respectively. Each signature matched what you'd expect from a comet, but this comet had been frozen solid in the space between stars for billions of years. Now, as it approached our sun for the first and only time, it was waking up. The nucleus itself appeared tiny through Hubble's eye, no larger than 5.5 meters in diameter, but estimates for the complete object with its coma ranged up to 24 kilometers across 100 times larger than Oumuamua, 10 times larger than Borisov, and it was moving faster than either of them. An ancestral ice bullet train hurtling through our cosmic neighborhood. But here's where things get complicated. The coma had a tail pointing towards the sun, not away from it. Solar radiation pressure should always push comet tails away from the sun, but 3IU Atlas was ejecting material so heavy the radiation couldn't push it. Massive particles just kept plowing forward by inertia alone like a cosmic shotgun blast aimed right at our star. The trajectory itself defied probability. Most interstellar objects should come from random directions, but 3I Atlas was traveling almost perfectly aligned with the plane of our solar system. Its path was inclined just 5 degrees from the ecliptic, the orbital plane where all our planets reside. Harvard astrophysicist Avi Loeb calculated the odds of this alignment happening naturally, 0.2% less than a 1 in 500 chance. Some speculated about artificial origins, the size, the trajectory, the apparent lack of detectable chemistry at first. But as the object warmed and outgassed, every measurement screamed comet, real ice, real rock, real chemistry from a real star system. Somewhere in the Milky Way's thick disk, which begs the key question, where did it come from? The velocity components tell the story. When 3I Atlas arrived in our solar system, it was moving away from the galactic center at 51 kilometers per second. It was also moving upward through the galactic plane at 18.5 kilometers per second. That vertical component is huge compared to nearby stars. It means this object is on a highly inclined orbit around the galaxy, the kind of orbit typical of thick disk objects, ancient stars, and debris from the Milky Way's earliest days. The thick disk is where the galaxy stores its oldest material stars with lower heavy element content than our sun planetary systems that formed when the universe was younger and different. 3 Atlas came from there. It carries with it the chemistry of a star system that may have formed 7 billion or more years ago, when our sun was nothing more than a gas cloud that hadn't even begun to contract. On October 30th, 2025, at perihelion 3I Atlas will reach its closest approach to the sun, 4 astronomical units, just inside Mars's orbit, moving at 68 kilometers per second, its maximum speed. Then it will begin the long journey back to interstellar space, never to return. Mars will have a front row seat. On October 3rd, the comet will pass within 29 million kilometers of the red planet, close enough for the Mars Reconnaissance Orbiter to photograph it with its high-rise camera at 30-kilometer resolution. The first detailed photographs of an interstellar visitor ever taken by another spacecraft. Earth will have to settle for a long-distance observation. Its closest approach to our planet will be in December, when 3I Atlas is already speeding away. 1.6 astronomical units, about 241 million kilometers, far enough to be safe, close enough to keep watching. But by then, the real show will be over. Until September 2025, ground-based telescopes can track it. Then it will pass too close to the sun to be safely observed. It reappears other side in early December, but by then it's already accelerating its departure. Soon it will be too dim to be detected. Another point of light fading into the cosmic background, except for what it leaves behind. Data. Chemistry. Proof that the space between stars is not empty. Proof that objects can survive billion-year journeys across the galaxy and still tell stories about their origin. Proof that other star systems eject material just like ours, and that material finds its way to places like this. The Vera C. Rubin Observatory went into operation this summer. Its wide-field survey should detect 1 or 2 new interstellar objects per year, which means 3I Atlas won't be the last visitor, just the most extreme. So far, the fastest, the oldest, the most eccentric, and probably not the weirdest. Colin Notgrass of the University of Edinburgh is leading the European Space Agency's Comet Interceptor mission, slated for launch in 2028. The spacecraft will wait at the L2 Lagrange point until a suitable target appears. Then it will deploy 3 smaller probes to intercept and study a comet up close. If another interstellar visitor arrives with enough advance notice, the Comet Interceptor could provide the first detailed analysis of material from another star system. But most interstellar objects will remain distant targets for ground telescopes, simply too fast to intercept, too dim to study in detail. 3I Atlas represents a unique opportunity large enough to observe clearly, active enough to produce detectable spectral signatures on a trajectory that brings it close enough to Mars for spacecraft observations. The next comparable opportunity might not come for decades or centuries. Most interstellar objects are likely much smaller than 3I or Atlas, dark, inactive, undetectable, until they're already leaving the solar system. We got lucky with this one and the most revealing, but 3I's Atlas holds darker secrets. The object's extreme velocity suggests a violent ejection from its home system. Normal planetary formation does not produce objects moving at 58 kilometers per second relative to their local stellar environment. Something catastrophic had to have happened. A close stellar encounter that disrupted the entire system, a supernova explosion that launched material across interstellar space, or the death throes of a massive star that went hypernova and scattered planetary debris throughout the galaxy. The age estimates support this violent origin story. 11 billion years puts 3I or Atlas close to the formation of the Milky Way itself. Back then, galaxy mergers were common. When massive stars lived fast and died young in spectacular explosions, when the interstellar medium was a shooting gallery of high-velocity debris from stellar catastrophes. If 3I Atlas is truly that old, it survived the most violent period in galactic history. It witnessed the galaxy's heavy element enrichment as successive generations of massive stars exploded and seeded space with carbon, oxygen, silicon, and iron. It may have passed through multiple spiral arms as the galaxy settled into its current structure. It certainly survived gravitational encounters with countless other stars during its billion-year journey to our solar system. The survival itself is remarkable. Most small objects are torn apart by tidal forces during close stellar encounters. They fragment into rubble piles or are completely destroyed. But 3I/Atlas remained intact enough to survive billions of years in the hostile environment of interstellar space. That suggests exceptional structural strength, or incredible luck, or both. Rotation data provides clues to its internal structure. A 20% variation in brightness over several hours indicates an elongated, non-spherical shape, probably twice as long as it is wide, similar to many comets in our solar system, but unusual for an object that supposedly survived billions of years of cosmic ray bombardment and micrometeorite impacts. Most interstellar objects should be heavily eroded. Their surfaces polished by high-velocity dust impacts their volatile materials depleted by cosmic ray heating, but 3I Atlas shows fresh cometary activity. Clean spectral signatures of water, carbon dioxide, and organic compounds, as if it had been protected in some way during its journey through space. Perhaps it spent most of those billions of years in a dormant state, frozen solid, at temperatures near absolute zero, with surface volatiles locked away under protective layers of non-volatile rock and dust, only awakening as solar heating penetrated deep enough to reach subsurface ice deposits. The outgassing patterns support this interpretation. Early observations showed little activity when 3I Atlas was still 4 astronomical units from the Sun. But as it moved within 3 astronomical units, the coma brightened dramatically. Water vapor production increased exponentially, as if buried ice deposits were finally reaching sublimation temperature. This late onset of activity is characteristic of ancient comets with highly processed surfaces. New comets from the Oort cloud begin outgassing much farther from the Sun. Their surface ice is fresh and sublimes easily. But comets that have made multiple passes through the inner solar system develop protective crusts that inhibit outgassing until solar heating becomes intense. 3 Atlas shows this old comet behavior despite being on its first pass through any star system in billions of years. This suggests its surface was already highly processed before it encountered our Sun. Cosmic ray bombardment and micrometeorite impacts had created a protective lag deposit that kept the interior ice pristine while the surface evolved into a non-volatile shield. The chemistry tells a complementary story. The water vapor detected by Hubble and the Swift Observatory shows isotopic ratios different from Earth's oceans, different from the comets in our solar system. The deuterium to hydrogen ratio is elevated, suggesting its formation in a colder environment with different stellar chemistry than our Sun's birth nebula. Carbon monoxide ratios are also anomalous, higher than typical solar system comets, but lower than interstellar ice detected in molecular clouds, as if 3I Atlas had formed in an intermediate environment, perhaps at the outer fringes of another stellar system, where stellar heating was minimal but not completely absent. The detection of nickel is particularly intriguing. Atomic nickel vapor is rare in comets. It requires high temperatures to vaporize metallic nickel from solid grains. Most comets don't get hot enough during normal outgassing to produce detectable nickel lines. But 3I Atlas was generating strong nickel signals even when it was still relatively far from the Sun. This suggests an unusual composition or unusual heating mechanisms. Perhaps the nucleus contains more metallic material than typical comets' iron-nickel grains incorporated during its formation in a metal-rich stellar environment. Or maybe rapid rotation and tidal stresses from our Sun's gravity are generating internal heating through friction and flexing. The forward-pointing tail adds another layer of mystery. Normal comets develop tails that point away from the Sun because solar radiation pressure pushes the tiny dust particles outward, but 3E Atlas was ejecting material too heavy for radiation pressure to affect. Large grains or chunks of ice that just continued forward on ballistic trajectories. This heavy particle ejection suggests violent outgassing events, not the gentle sublimation typical of most comets, but an explosive decompression as subsurface ice pockets suddenly reached vapor pressure, like underground chambers of pressurized gas, suddenly venting through surface fractures. Explosive outgassing could explain the unusual dust production rates. Hubble detected dust loss consistent with comets much closer to the Sun, but 3I Atlas was producing just as much dust while still at Mars's distance. It's either far more active than normal comets, or it's ejecting larger particles that carry more mass per unit area. Both interpretations point to internal processes unlike anything in our solar system. Perhaps billions of years of cosmic ray bombardment had created subsurface chemistry that becomes unstable when heated. Radiolysis products that decompose explosively when they reach certain temperatures. Exotic ice phases that undergo rapid phase transitions under solar heating, or perhaps the nucleus's structure itself is unusual. Instead of a solid monolithic body, 3I Atlas could be a collection of smaller, loosely bound fragments, a rubble pile held together by weak gravity and surface ice cementing. When solar heating weakens the ice matrix, entire sections could break off and vaporize rapidly. The brightness variations support the rubble pile hypothesis. A solid rotating body should show smooth periodic changes in brightness, but 3I Atlas shows irregular fluctuations superimposed on the main rotation signal, as if pieces of the surface were constantly shifting as material is ejected and the internal structure rearranges. This dynamic evolution makes 3I Atlas particularly valuable for understanding the physics of interstellar objects. We are observing in real time how an ancient relic from another star system responds to solar heating for the first time in billions of years. Each observation reveals new details about how these objects survive their galactic journey and what happens when they finally re-encounter stellar radiation. The timing is fortuitous. Advanced space telescopes like JWST and Hubble provide unprecedented spectroscopic capabilities. Ground-based observatories have better sensitivity and resolution than ever before. We are studying 3I Atlas with instruments that didn't exist when previous interstellar visitors passed through, but the observation window is finite. After December 2025, 3I Atlas will be too faint for detailed spectroscopy. The chemistry will remain locked in the data archives. Future visitors might be smaller, darker, less active. We might not get another chance like this for decades. In 2026, archaeologists working at a radio telescope site in Chile will discover foundation stones marked with precise coordinates, not for any earthly location, but for a point in space where 3I Atlas first entered our solar system. On July 1, 2025, at 4.5 astronomical units from the Sun, the exact spot where humanity got its clearest view yet of the chemistry from another star system. The first confirmed comet from the galaxy's thick disk proof that the universe has been building, destroying, and rebuilding worlds for longer than we ever imagined. Cold calculations, ancient ice, billion-year journeys, M.